Okay, so it started now, and let's see, I'm gonna share the slides through. Okay, cool. So let's see. We're gonna do. Right, so we're gonna continue the discussion on the maximum likelihood. In particular, so last time, a little slow over here. All right, I think we're roughly around here. Yeah, last time. Okay, right. So last time we looked again the Fisher information. Okay, so there are two ways that you can do the definition, and most of the time people would go with the second one in order to find the actual Fisher information of the model, right? Okay, so we looked at an example of the Poisson. And I want to show you again this result. So this is a theorem, the proof is not required, but we should know that asymptotically, so if you have like a large sample size, the theorem guarantees that the, you can write it in two different ways. You can either, so this is the way that the textbook presented, the first one. And this, so that is to say, this is the MLE minus the truth, and then multiply with some variance, or like 1 over variance over here, follows a standard normal distribution, okay? But you can also rewrite it as theta hat, so this will be the MLE, follows a normal distribution, center at the truth, and then the variance is 1 over n times the Fisher information. So that's why we need to know how to do the Fisher information in order to say, if we want to find the confidence interval, say later you're gonna see, because once everything follows approximately normal, we'll be confident that we can have a confidence interval through the normal theory over there. So you'll see that why Fisher information is gonna come in. So in this case, once we have the theorem in this way, we're gonna say the MLE is asymptotic unbiased. So this asymptotically really talking about large sample theory. Okay? Every time you hear this term, it's gonna about, I think it's gonna be about large sample theory. And then because this 1 over n times the Fisher information is the variance for this normal distribution. So we also call it the asymptotic variance of the MLE. Okay, so these are just some definition. And so with this, you will notice that we're able to construct confidence interval about the MLE right now, right? So earlier we learned about how to do MLE, like using the, like getting the likelihood and then get the log likelihood, take the first order derivative, set it to be 0 to solve for MLE, but that's only a point estimate, right? So through this theorem, we'll be able to come up with a confidence interval, which gives us a range of values and also provides some uncertainty about the parameter. So we looked at MLE before, confidence interval before. So just a little bit review and preview of what we're trying to do over here. So confidence interval, again, is based on the sample values used to estimate the parameter. This is back in chapter 7, we're talking about it. Because the samples values are random, so the interval is random, right? That's why like a 95% confidence interval is if you construct about 100 different times, about 95 of them are gonna cover the truth. So each confidence interval is random. And the coverage probability is just a formal definition over here. It's the probability that the CI contains theta. So if you're doing a 95% confidence interval, then you're doing, the coverage probability is 95%. Okay? So this is what we know before. And let's see how we can do it for the MLE. So there are 3 methods that the textbook talks about. So the first one is exact methods, and that goes mostly only for normal because you can have all of the theory over there, but it's very exceptional in the case that usually you won't have the exact methods, like you don't have the analytical solution for that. Okay? So for our course, we're gonna focus on how to do the approximation. And the approximation is based on the large sample properties of the MLE, just like what we have seen before. So asymptotically, the MLE follows a normal distribution centered at the truth, and the variance is 1 over n times I, right? The Fisher information. So we're gonna use that to come up with confidence interval. And the last method is bootstrap. We have looked at it multiple times already. So bootstrap can always get you some kind of confidence interval there. Okay? So for us, let's just focus on number 2, because number 1 is very exceptional, like you don't really see it that often. And number 3, we covered in other approaches before. Right? So this should be pretty straightforward, because we know that from the large sample theory, we know that the MLE asymptotically follows a normal distribution centered at its mean, theta 0, and the variance is 1 over n times the Fisher information. So we can rearrange the terms and then get the confidence interval in this way. Does that make sense? Yeah, so pretty much you will have, you're going to construct a confidence interval at the MLE. That's the middle point. And then you compute your variance. And then if it's a 95% confidence interval, you minus 1 times 1.96 times the standard error, which is the variance of the normal distribution that we know. And then you're going to do a plus on the other side. And then you're going to get a 95% confidence interval. So eventually you're going to get something like this. Okay? So we're constructing a confidence interval around the MLE. Right? Just like we're constructing a confidence interval around the sample mean, right? So now we have a point estimate, MLE, plus or minus. So this is the z-score of whatever confidence level that you're looking at. And then over here, this is the standard error. Right? So remember back, like last time, we looked at how to find the MLE as well as the Fisher information for Poisson distribution. So let's just all do one exercise over here to figure out how I can come up with, say, what is the theta hat? So theta hat over here are the generic parameter estimate, right? So if we're doing Poisson, so let me try a different, let's see. Let me try a different option over here. Okay, so remember the Poisson? Let's see, I have to sit down, sorry. Poisson lambda, right? Right? First, we're gonna get there. I'm gonna get a bigger iPad at some point. This is too small. So what is the PMF again? Anybody remember? All right, so x equals to x will be lambda x, right? E to the negative lambda, and then x factorial. Oh my God, factorial. Okay, yeah. So remember we showed it before, so we won't do that exercise now, but at lambda hat, the MLE is x bar, right? X bar. Yeah. And the feature information, last time we looked at it, if I remember it correctly, I think is 1 over lambda, right? So with all of this, what you're gonna do in order to come up with the confidence interval. So try to write it down right now for here, because I cannot write too much on this board. So we're gonna remember this, and then, let's see. And then I do a different one. And so, okay, so from that, we know the MLE is x bar. X bar. And then Fisher information is 1 over lambda. And we know that asymptotically, the MLE gonna follow a normal distribution centered at lambda, and the variance is 1 over n times the Fisher information over here. Sorry about the closing parentheses, we probably won't be able to get it. But this is what we know just now. So how can we get a confidence interval? So this is a practice for the Poisson case. So please try that, and I will try to sketch it over here as well. So let's see. Okay. Let's do a 95% confidence interval, and you can just use 1.96. Okay. So it's gonna be the MLE. to get the first form to work. So it's going to be centered at the MLE lambda hat plus or minus 1.96 times the standard deviation over here. So what is the, so because x bar is the MLE, right? So that will be MLE plus or minus 1.96 times 1 over n times 1 over x bar, right? Because earlier we just showed that the feature information I lambda is 1 over lambda. So I lambda hat will be 1 over x bar. Oh, no, it's wrong, right? Yeah, thank you, yes. It should be, let's see. Let me get it straight again. So because, let's see. Okay, because earlier we said that feature information I lambda is 1 over lambda, right? So now the feature information at the MLE, so it's I 1 over x bar. That will be 1 over x bar. So the feature information is x bar over here. Yeah, let me try to erase the upper part so I can show you what I'm trying to say. Okay. So what we know earlier on the top, I'm going to start to write, is the MLE, oh sorry, the feature information is 1 over lambda, right? So the feature information at the MLE will be x bar.
Square root inside the
Do we need one? I don't think. Okay, so right, let's see. Okay, so Hui's question is, so okay, let me try to erase this part to see if I can do it. Okay. Yeah, so okay, so the asymptotic results, let me just get it. I'm just gonna write it again. Okay, the asymptotic results was, let's see, theta hat follows approximate low normal at theta 0. That's the truth, and then the variance is 1 over feature information. Okay, so the variance is 1 over n times the feature information at the truth. But so then the standard deviation will just be the square root of that. And one more thing, maybe you, when you're doing it, maybe a little bit confused is we start. So if you look at the middle one over here, the feature information is evaluated at the truth, right? I theta 0, but we don't know what it is. So when you're actually constructing confidence interval, you're using the MLE to approximate that. So that's the jump over there. Okay, so let's see this. So we start with the middle one. That's the asymptotic results for the normal approximation for the MLE. And then we go to the first line over there. That is what is for the Poisson case, right? Feature information is 1 over lambda. And then so feature information at the MLE will just be x bar. And the last line over here is to actually construct the confidence. Make sense? Or no? Right. Yeah, let me just try it one more time. Let's see. Okay, Poisson, so something we know. The MLE approximately follows a normal distribution centered at the truth with variance 1 over n times feature information, okay, at the truth. Okay? So for Poisson, MLE is 1 over, no, it's x bar, right? And feature information, we showed it last time, is 1 over lambda. So we will have the confidence interval, 95% to be, so it's centered at the MLE, so it's x bar, plus or minus 1.96 times the standard deviation of the normal, right? And the standard deviation is 1 over n times the efficient information at the MLE, which when you do the math, it will be this, right? And then when you bring that up to the top, let's see if this can be good enough to do that. Okay. There's a bar, it's gonna come up, right? Yes. Okay. Yeah, so this is how you're gonna do a confidence interval around the truth, like for the truth around the MLE. It just happens that for Poisson, the MLE is at the root. Okay. It's the sample. Right, so this actually reminds me of the question that Woodruff the other day asked about. So for Poisson, remember, we're saying that Poisson, the MLE is X bar. So MLE is the sample mean, right? So whatever, like the asymptotic distribution for the MLE that's going to follow, that's what we showed just now, it's going to be the same from the results from chapter 1 for sample. And so last time I was saying that maybe it's a special case for Poisson, and then later I went back to think about it. It is because for Poisson, the MLE is the same as the sample mean, so these two results are the same. Okay? So in the future, if you come up with any, say for certain parameter, for certain probability model, if you have an MLE equal to the sample mean, then whatever results that we have for the sample mean from chapter 7 going to be the same as whatever results you're going to have for the MLE. Okay? So that's a really good comment the other day, I think. All right, sounds good for this? Okay, cool. So let's go back to the slides. And okay, yeah, so I left a, so this is what we stopped just now. And I also inserted like example on the exponential case, which we won't go through now, but I provide all of the solutions over there just as a demonstration with the data set that we started looking at. Yes. Sure. Give me a second. Are you talking about this one?
Yeah. There's another.
Oh, that should be my mistake, I think. Sorry about that. Yeah, there shouldn't be a, yeah, my bad. I don't think there should be a square root over there. Thank you. Yeah, I will clear that. So it should just be what I just showed earlier with the writing point. Okay. Yeah, thank you. Thank you both. I think that's why we was asking the earlier question. So, so no, if you look at like the results, the asymptotic results for the MLE, like the first row or the second row over there, then the sample, yeah, like the square root over here, this will be the standard deviation, right? Yeah, because if you bring it back over there, because think about if it is a constant, if you bring it back into the normal, it will be the square of that. And that would just be the variance. So this is the standard deviation. So it's a typo over here. I'm gonna get rid of this square root over here. Yeah. Thank you. I guess that's why I was confused earlier. All right, so I will leave you to just use this exponential exercise. It's really working through the steps, and it's very similar to the Poisson that we just see. Except over there, you have a different MLE. You're gonna have a different diffusion information. But once you have all of that in place, you will be able to construct a confidence interval for the parameter around the MLE. Okay. All right, so the next topic, like we have just 2 more over here. Hopefully let's finish it today. So efficiency is an idea that we actually talked about a little bit. Like I tried to motivate you all thinking about if you have 2 different estimators, how are you gonna decide which one is better? So there is something called mean square error that people like to use. So let me show you what it is first. So it's at the bottom over here. So the mean square error, by definition, is the mean square error. In particular, once you expand the terms, you will notice that a mean square error of an estimator, theta hat, is the variance of that estimator plus the bias of that estimator. Okay, so let's look at the 2 terms breakdown over here. MLE theta hat, don't worry about the middle term, that's the definition, but then once you expand the term, it's going to be the variance of this parameter plus the bias over there. And the bias makes sense, right? It's like the difference between the expectation of this parameter with the truth and take the square. So these are what these two terms are about. So you see that the MSE, mean square error, is really trying to measure, say, how well the particular parameter estimate is centered around the truth. It's the variance plus the bias. So if it is an unbiased estimator, say theta hat, then the expectation of theta hat will be theta 0, then the MSE will just be the variance. Right? So pretty much that means this term goes away, and then the MSE will just equal to the variance. Okay? So if you have two unbiased estimators that you want to compare, because they're unbiased, compare their MSE just becomes comparing their variance, which is what we have been doing in a sense, right? We're trying to think about for different parameters, for different estimators, if both of them are unbiased, we only need to compare the MLE, that variance of that. Make sense? Yeah, so this is just building up for what we're trying to, like this is a particular measure that people like to use. And in particular, so from there, the definition of the efficiency will be, if you're looking at two estimators, theta hat, like theta 1 hat and theta 2 hat of a true parameter theta, the efficiency of theta 1 hat over or relative to theta 2 hat is defined to be the variance of theta 2 hat over the variance of theta 1 hat. Okay? This is definition, and I want to ask you now, if I have an efficiency of theta 1 hat and theta 2 hat, if it is larger than 1, which one is a better estimate? So say EFF theta 1 hat, theta 2 hat, that thing is larger than 1. Which one is a better estimate here? Theta 1, right? Because you're going to have a larger, because it's larger than 1. So variance of theta hat 2, theta 2 hat is larger than theta 1 hat. And notice that if I try to compare it in that way, I'm kind of making the assumption like, so in the definition, they didn't say that you should compare like the unbiased estimator, because this is true for everything, for unbiased or unbiased estimator. But if you're really trying to just say, if we're really comparing to like variance of theta 2 hat over variance of theta 1 hat, only if both of them are unbiased, this kind of comparison is useful or meaningful, right? So that is the thing that, first of all, pay attention is the ratio. So it's, first of all, it's a theta 1 hat comparing to theta 2 hat, but it's variance of theta 2 over theta 1. So if it's larger than 1, theta 1 is better, okay? So it's a little bit, it's just, I think sometimes like the way that it's written might not be that intuitive. And the other one, the second bullet point over here is, yeah, the case if it's larger than 1, then we should choose theta 1. But again, this is only meaningful if both of them are unbiased or they have the same bias, right? Because overall, we want to compare the MSE, the mean square error. And then we know that it's a breakdown of the variance plus the bias. So comparing the variance only makes sense if the two estimators have the same bias or no bias at all. Right? Make sense? Okay, cool. So down here, I put in one extra comment over there. Most meaningful when both estimates unbiased or have the same bias. Okay? So this is, yes, so this is efficiency. And we will see that at certain, under certain circumstances, the MLE is efficient. Okay, so overall, like why we're trying to learn so much about MLE is because at certain point it will be efficient. Yes. Okay. So one last thing over here is if there is a lower bound of the variance of any estimate, then the lower bound can be used as a benchmark, because if one estimate comes along and we can show that the variance reach this lower bound, then it is optimal because you cannot improve it anymore. Okay. So for unbiased estimator, there is this Cramer-Rao inequality, which shows that for any unbiased estimator, the lower bound, like the smallest variance that you can achieve, is 1 over n times the Fisher information. Okay. So one more definition over here. this Cramer-Rao inequality tells us that if you have an unbiased estimate of the parameter, you will have the lower bound, the lower bound of the variance that you can do. So you see that it's the variance, so T is the unbiased estimator, so variance of T is larger or equal to 1 over n times the Fisher information. Okay? So this is to say, if you have a unbiased estimator, and if you can find for that particular unbiased estimator, its variance reaches this lower bound, then you cannot improve this estimate anymore. It's the best one in a way that we're gonna say it's efficient. Okay, so remember, like we just define efficiency between compared to estimators, and then over here for an unbiased estimate, if it reaches this particular bound, you know that like it's good, it's the best you can get under these circumstances. Okay. So the textbook does provide a proof, but I'm not gonna require it for you to know for this class. It's a little bit complicated over there. But I do want to motivate you to think, based on this form, remember where did we see this before? We just saw it for the asymptotic results for the MLE, right? So you will see that, so soon I'm gonna show you, because you see like the lower bound is 1 over n times the Fisher information. So we know that the MLE asymptotically gonna have a variance like that, similar to that, right? So under certain situations, MLE will be efficient. Make sense? Yeah. So this is what we know earlier. So this is exactly just now we're trying to show practice with the Poisson case. And then, for any unbiased MLE, then there will be asymptotically efficient because it's going to reach the lower bound. Yeah. However, MLE are not the only asymptotic efficient estimates, and also possibly, even if you find an MLE that reaches this lower bound, you might still find some biased estimator that has a smaller mean square error. So you might still want to choose that. Okay. Yes?
How do you make sense of which is more important, biasness or the variance?
What do you mean?
Like, supposing that we have an estimate with like an MLE.
Yeah. So for us, we should say like either you compare both unbiased estimator or having the same bias. So in this case, so I'm just saying that it's still possible that you're going to have a smaller MSE, even if you have an unbiased estimator, because your variance, so for a particular, I don't know, theta tilde, you might have a super small variance over there, but it's biased, right? But I'm just saying that if right now we're looking at two estimators, both of them are unbiased, then you should compare their variance, right? Because the efficiency, like the idea over there. And then furthermore, because of this asymptotic, because of the lower bound that we just showed, we know that any unbiased, so it's any unbiased MLE gonna be asymptotic efficient because it's gonna reach the lower bound. So for Poisson, you will see that Poisson is actually an example that it can, like the MLE is asymptotic efficient because it is unbiased and also it reaches the lower bound. Yeah. So maybe let me get to this point over here. Yeah, so Poisson, you see that we have been working through this for multiple stages. So we looked at the MLE, the Fisher information. Just now we looked at how to come up with the 95% confidence interval. And then if you do the lower bound for Poisson, you will notice that it's lambda over n, which again reaches the lower bound. So for Poisson, it's unbiased, and then it reaches the lower bound. So it is efficient, and it's pretty much like the optimal that you can have for the Poisson model, the MLE. Okay. So, like I highlight over here, that is to say, if you compare the pool of all unbiased estimators, the MLE will be the best because it reaches the lower bound. Okay. If you compare the pool of all unbiased estimators, you only need to care about the variance, right? And the variance is a lower bound by this Cramer-Rao lower bound theorem, and MLE reaches the lower bound. So MLE is the best among all of the unbiased estimator. But it doesn't rule out the possibility that there might be some biased estimator out there having a smaller mean square error. So we can only say that for the Poisson case, say, MLE is the optimal because it's unbiased and it reaches the lower bound. Does that make sense? Or no? Any, like, what's the confusion here? Yeah, let's see. Let me just try one more thing over here. All right, so MSE is the variance plus bias, right? Yeah, so we know that if you want to compare only the variance between two estimators, then only if they're having the same bias or no bias, then comparing the variance makes sense, right? So say now, we're only looking at unbiased estimator. Okay, so if we're only looking at the pool of unbiased estimator, we're gonna only compare their variance, right? Whichever has the smaller variance will be the better estimate, okay? So because of this Cramer-Rao lower bound for unbiased estimator, so notice that we highlight that the Cramer-Rao lower bound is only for unbiased estimator, and that variance is the smallest amount is this, right? And this looks very similar to the variance of the MLE that we have been trying to derive earlier, right? So I'm just trying to say that if you're looking at two unbiased estimators, theta 1 and theta 1 hat and theta 2 hat, if you find one estimator that the variance can reach the lower bound, it's the best, okay? Because that's the lowest among all of the unbiased estimator, that's the lowest you can get. Okay? So for Poisson, MLE is, what is again, X bar, right? X bar, if you look at this, by applying this Cramer-Rao rule over there, you will notice that it reaches the lower bound and it's unbiased. So that is to say for Poisson distribution, the MLE is unbiased and it reaches the lower bound. So it is asymptotically efficient. Because efficiency, remember, we're comparing two different parameters, two different estimators and looking at which one is smaller. So for MLE, you will get to, let's see, let me get it back to that. Yeah. So for the Poisson case, you will be able to get that. Okay. Make sense? The logic flow. So in the end, I will try to summarize again, like what are the steps that we're trying to do. But it's just, I think there is a lot of like theorem and information all come together. So it's a little bit hard to sort it through. What is the logic flow? But really we start with MSE, which is variance plus bias. And then we have to control the same bias or no bias at all when we're comparing two. So let's just look at all of the ones without bias. So all of the unbiased estimator, we only need to compare their variance. Okay? And then among all of them, whichever has the smallest variance will be the one that we're gonna go for. Right? And then for any unbiased estimator, the Cramer-Rao inequality gives us a lower bound. So whichever, lower bound of variance. So whichever reaches that lower bound, gonna be having the smallest variance. So among the pool of unbiased estimator, that will be the best one we're gonna choose. So for Poisson case, the MLE actually, it is the only one. Like I should say, it is the one that's gonna be reaching the lower bound. Okay, so over here in red, so no unbiased estimator of lambda can have a smaller variance, okay? Comparing to the MLE, because MLE already reaches the lowest. And also, so in this case, the MLE X bar is optimal for the Poisson distribution. However, because after all, we still like the bigger one that we start with is the mean square error, right? Mean square error is variance plus bias. So it's still possible that there's some estimator out there having a smaller MSE, but it's biased. Okay, so this is just saying that we couldn't rule out the possibility that out there can be a biased estimator having a smaller MSE than X bar does. Okay? But MLE is the best among all of the unbiased estimator. Because unbiasedness is also important, right? Like who wants to have like a biased estimator all the time, even though you have a smaller MSE, right? So there are a bunch of things that we have to take into account when we're doing this. And just so you know, so when I was prepping for this part, I was doing like everything. Remember, like I started using exponential as an example, and then up until I reached this point, I couldn't use the example anymore. Because if you go back to check, the MLE of the exponential 1 over x bar is actually biased. Yeah. So in that way, I couldn't even show using the Cramer-Rao inequality to show that it's the asymptotically efficient estimator. Okay. So that's some lesson that I learned as well. I was trying to do it and I couldn't get it. I was confused, and then I go back again and I realized the textbook only talks about the Cramer-Rao lower bound for unbiased estimator. There's a version out there for biased estimator as well, but we don't gonna go there. Okay, so this is the case. So that's why in the end I started using like Poisson most of the time, because it's a worked out example throughout the book that talks like pretty much satisfy every steps that we're trying to go through. Okay, however, exponential distribution unfortunately is a biased estimator, the MLE. So the Cramer-Rao bound doesn't work out for it because we cannot reach that, because that lower bound is only defined for unbiased estimator. All right, one last thing. If you get a sample and you know what the distribution, this probability, what kind of distribution the sample is following that you're putting on, the probability distribution, then if there is a statistic, which is a function of all of the random variables, is there a statistic like that can contain all of the information in the sample about the parameter? So if you can find something like that, we call it as the sufficient statistic. So if you can do that, then you can only just look at the sufficient statistic instead of the entire data. Okay, so let me show you the definition first, and then let me ask you how to use the Poisson case to do it. So say a statistic T, which is a function of the data, is said to be sufficient for the parameter if the conditional distribution of all of the data point or random variable, given the sufficient statistic, does not depend on theta anymore. Okay? So by this definition, if you pause and think about this a little bit, it's really trying to say that if you can find a statistic that can contain all of the information from the data, then we can only just look at the statistic. We don't care about each data point in a way, because that statistic can tell us everything about the parameter that we're trying to estimate. Okay? So don't worry if you still feel confused here, but let's get to here, again, using the Poisson case. To find the sufficient statistic for the Poisson, you will see that we're gonna first write out the joint likelihood over here. And I want you to think about here, based on the definition of the sufficient statistic, what would be one statistic over here that if you know it, you don't even need to know about all the data point, because knowing that statistic can give you everything that you need to know about theta. So I'm just trying to say, this is the joint, okay? Everybody do this. This is just provided to you right now. And based on the definition that a statistic T is said to be sufficient for theta, so in this case, a statistic T is said to be sufficient for lambda, because we're looking at the Poisson, if the conditional distribution of x1 to xn given T does not depend on lambda for any value of T. So in that joint distribution, what do you think will be the statistic that if we know it, everything, and then conditioning on that particular statistic, everything we know, like the whole, let's say, the conditional distribution of this given the statistic does not depend on lambda. So maybe I can start a little bit, probably not this one, because this one doesn't really interfere with lambda, right? Because we're trying to look at the conditional distribution of x, all of the x given the statistic. So knowing or without knowing this doesn't really affect lambda in a way, right? So we're left with the top. Which one you think will be the one that is the sufficient statistic here? Yeah, so lambda, the sum of all of the xi, is really where the data is I should say intersecting or interacting with the parameter over here, right? So lambda raised to the sum of all of the xi. Over here is a little bit as well, because you need to know how many data points are there. But in this case, let's just assume that we know it. Like n is given, say. So in this case, if you know what the sum of all of the xi is, then you know everything about the contribution of lambda to the joint. Does that make sense? Yeah, so let's pause a little bit over here. Yeah, so it is indeed, the sufficient statistic here is the sum of the xi. And let's plug that into the definition, if that's true. Okay? So the definition is saying that a statistic t is said to be sufficient for lambda if the conditional distribution of xi, given the sufficient statistic, does not depend on theta or depends on lambda anymore. Okay? So if you look at, let's look at here. So they're talking about the conditional distribution of x1 to xn, given not lambda here, it's given the t, right? So it's going to be given this this sufficient statistic over here. Once you're conditioning on that, conditioning meaning that we know this, right? If you have a conditional probability or conditional distribution, if you know the sum of all of the xi, then you know everything about the contribution of lambda over here, because it's raised to the power of the sum. And then this is just from the data, but it's not really interacting with lambda, so we don't worry about this one. Does that make sense? So, I mean, this is one way if you think about, so definition, again, sometimes just like we have seen with Fisher information, the first definition is intuitive because it's the variance of the score, but it's very hard to do. So we go to the second definition, which takes the second order derivative and take the expectation and then take the negative, and it's much easier to do over there. So just so you know, there's another theorem out there that can help you to find the sufficient statistic much easier. So you see how they factor things. It's a factorization theorem, actually. So the joint distribution can actually be into G. So G is a function of the sufficient statistic and the parameter times whatever out there is about the data. Okay? So if you do that, let's try to write out, for the Poisson example over here, what is your G and what is your H? Because once you do that, it's much easier to identify what is the T over there. So let's pause here a little bit to think about what it is. The joint is lambda raised to sum of xi, exponential negative n times lambda divided by the product of all of the factorial. So if we want to factorize this into two components, G, a function about the sufficient statistic and the parameter, and then the other one is whatever that is left out there about the data, which is not interacting with the parameter, and then we're going to put everything into H. And then once you find out this two, it will be easier to realize what T is, because it's going to be like the statistic that is interacting with theta in the joint distribution. Okay. So what do you think? I'm just going to walk around. Oh, I forgot to give this to you when you're asking questions. Next time. Yeah, so then from here, this will be sufficient statistic. Right? Mm-hmm. I guess it's maybe more intuitive to look at this way. Mm-hmm. So H will be whatever is not interacting with the parameter for the joint, and G will be whatever the data and theta is combined. Okay? So if you do that, you will see that, I think, the G in this case will be lambda, so everything on the top. while H just will be the part that is about the data, but not about the parameter. So if we put it into this two forms, I think, and then we know that this is a function about the sufficient statistic and the parameter, then the sufficient statistic will just be sum of the xi. Yes?
Shouldn't the H be 1 over what's written there?
Yes, H should be 1 over that. Thank you. Yeah, I will correct that. So indeed, yeah, in order to have the product of G and H to be exactly the joint, I should have 1 over here. Okay, I will correct that, but good point. Right, let's just don't worry about the last one. So let me just go to the summary and let's call it a day. So when we're describing, remember when we're describing how to choose one over the other, we're looking at two estimators, we're comparing their MSE, okay? But also we're looking at the efficiency of one of the other, which is the ratio of the variance. It is only useful or meaningful if you're looking at two estimators having the same bias or no bias at all, okay? So that's how we motivate it at the beginning. So the Cramer-Rao inequality over here is trying to tell you that for any unbiased estimator, you're gonna have a lower bound of the variance. So among all of the unbiased estimator, if your variance can reach that lower bound for that particular estimator, you're good, because that's the one that you want to go for. Okay. And that is defined to be efficient. So let's see. Don't worry too much about the Rao-Blackwell. I don't think I'm going to cover that. And so lastly, just talk about the MLE, because we've been talking about maximum likelihood for likelihood estimate for so long. We know how to do it. We know how to find the Fisher information, et cetera, et cetera. So for MLE, first of all, it is a function of the sufficient statistic. So therefore it is a sufficient. So the MLE will be sufficient, okay? But also, we looked at that as efficient if it is unbiased and also reaches the Cramer-Rao lower bound. So in that case, MLE is sufficient and efficient. Okay? And lastly, because of the asymptotic theory, the large sample theory for the MLE, we can actually quantify their uncertainty through constructing confidence intervals. So that's, I think, for the frequentist approach for parameter estimation, that's why people always like to go for the MLE. So remember at the beginning of the chapter, we're talking about you can use method of moments and method of MLE. And back then I was saying that like MLE is more popular because it has certain good quality, qualities or properties out there. So first of all, it's always sufficient because it is a function of the sufficient statistic. However, only if you're looking at unbiased MLE and also it reaches the Cramer-Rao lower bound, then it's efficient. So remember Poisson, it's true because it's unbiased and reaches the lower bound. However, the the exponential distribution, the MLE is not unbiased, so it doesn't satisfy that. But at least it's still sufficient because it will always be sufficient. And the last step over here is for any kind of MLE, unbiased or biased, you will always be able to get some quantity about the uncertainty about it. Okay? All right, sounds good. So I think, yeah, we're gonna end over here. And so that means on Friday, we can finally start chapter 9. And I sent out an email last night. If you think like some of the answers of your lab 1 is correct, just bring it to me. I can just regrade it because I think when I write it out, especially for the last 2 questions, you can either use the estimated standard error or the actual standard error. So that's why I think I only provided 1 solution, and then the grader just go with that. And then, but you can always use the other alternative, try to come up with the answer to those 2 questions. So if you can bring it to me, I can just collect it today, and then I give it back to everybody on Friday, and just explain that again. Okay? Yeah. If you forget to bring it, it's okay. We can, yeah, give it to me on Friday. I can always grade it. Yeah. So you can just leave it to the front, and yeah, I think that's all. So on Friday we're gonna start chapter 9. I will clear all of the typos and then upload the slides again, so we're all on the right page. Give me a second. I just need to make sure that I